Today's exam review class. You can find this lecture note on Canvas if that's easy for you to take lecture notes. So exam is on Wednesday night and it's still 7 to 9, 2 hours exam if you don't have like extra time allowed. So it'll be similar like 4 calculation problems. Again, those calculation problems they are very closely related to our example problem in class and homework practice. So I would say it's almost in the same level. My promise is that if you can solve all the example problem in class and you can solve the homework problem, like all these problems by yourself, you would do well in the exam. There'd be no surprise kind of question, no like ask you to be creative kind of question. So it's really close related to our lecture notes and homework problems. Um, so before I start, any specific question about the exam or anything you want me to do first? Question 3. Okay. From homework 19. The different variation finding Q. Okay, sure. Sure. I actually received the email yesterday also asking about this question, so I put a solution here. And of course, let's do it step by step. First, similar as what we did in the class for this one, we always separate X component and Y component and see what X component can cause and what Y component can cause, and we'll list A, B, C. But of course, I can ask D, E, F, it's the same. And list A, B, C point what kind of stress they have, and then your calculation, you will not miss any component or you will not have like extra component that should not be there. So same thing here. We separate these 3 forces. And let's start from this black color. In the X direction, in the X direction, if I define this X, Y, and Z, but of course, this problem can also be solved without different definition of the coordinates. You can really define the X, Y, Z in any direction you want. So let's assume that X direction is X direction and upward Y direction, and then of course, right-hand rule is the Z direction. Then we have for the actual force, well, it generates tension. Normal stress generate tension is uniform distribution of the mute microphone. Thank you. So the normal stress generated by tension is uniform distributed of the entire cross section. So sorry, it's the same F of A of ABC at ABC point. This one is easy. Second one is 500. I use a red color. So this 500, of course, will generate a transverse shear. This is if you are considering this plane. This is a transverse force, right? So it has transverse shear in the Z direction. So this one, of course, we talk about the stress distribution on the rectangular cross section. The derivation is quadratic change is maximum on top and bottom surface. Make sure that when it's in the Z direction, then this is the top surface, this is the bottom surface. Sorry, minimum. They are 0 at these 2 surfaces, which means that C should be 0, even though there is a transverse shear force on this cross section. But stress at C point, this tau, that C point should be 0. And we have some magnitude at B, and A point is on the neutral surface, should be maximum. Maximum, we already derived the equation, and B is something you guys want to ask. So, it's fine. I'm okay with. My cat is here also, but she's sleeping here. So now for shear stress, probably this is something that you guys want to ask, like how to calculate the shear stress at point B. And this one, as I said, for anything that is not like neutral axis, because that one I already derived for you. For anything that here or here and here, I can ask any point you need to use. Go back to VQ of IT. I will show you very soon. And for this one, of course, it will also cause a bending about the y-axis is my. And so now C becomes the maximum point. It should have the maximum normal stress. A becomes the neutral surface 0. B point is somewhere in between. This is in the calculation my of I. Now this distance becomes y, right? The distance between the neutral surface and this B point become the y. So of course, this one is much easier to calculate than like shear stress, because shear stress VQ, you consider area, you can consider y bar. Now let's back to the blue one, 750. Then this 750 is in the negative y direction, and consider this plane. Of course, it is a transverse force, so of course it has transverse shear. But thing is that since A, B, C, all 3 points, they are on the top surface, because if you apply a transverse shear force, transverse force in this way, this becomes the top surface, this becomes the bottom surface, and the quadratic change in between. So A, B, C all on the top surface. So even though there is transverse shear in the y direction, shear stress caused by this transverse shear force, they are 0. But of course, if I can change the point to any point I want. So let's say I draw a cross section here and I put some point in between, then it's not 0. Then you need to calculate, right? This one also called the bending moment. It will bend about y-axis, and since this is the force, now this becomes the moment arm. Be very careful when you like some force generated bending moment. Very careful what is the moment arm. So for example, for this one, it will generate bending moment about y-axis. This is a moment arm if we are considering ABC. But for 750, this force is generate bending moment about z-axis. Now, this is the moment arm considering ABC point. So don't get confused of the moment arm. When we grade your exam or like anything, we do the particularly. So every time you make moment arm wrong, there's some penalty. Every time you make some, yeah. So be very careful. So for now, this bending about Z, and of course, bending about Z point, about Z axis, A, B, C, they're on the top surface, all of them maximum tensile. So now after we have done this, the rest part is just calculation. So I would considering this part is the most important part for calculating this type of question. If you're clear about this, it's unlikely you will make a mistake. But if you don't do this, this is not required for any like solving homework, solving quiz, solving exam. But this is the key point, that make sure that you won't make any mistake to miss any component or add some extra component that should not be there. So now we have this one very clear for the A point. Now let's check. For normal stress, it comes from 3. Tension from this 10 kilonewton, bending from 750, right? These are 2 normal stress components. Of course, how to calculate M bending moment about y-axis, bending moment about z-axis, and moment inertia about y-axis, moment inertia about z-axis. This is something you can check later. I will post this one very soon after class. So for point A, the normal stress has 2 components: tension, tensile stress, bending on the top surface, tensile stress. Tensile stress plus tensile stress. We have positive normal stress at point A. And at point A, we also have a shear stress caused by this 500. And point A is easy because it's on the neutral surface. So we already have the equation derived for you. 3v over 2a. This is the equation we derived for narrow rectangular cross-section. And neutral surface, 3v over 2a, the equation you can use directly. You can use directly in your exam. So 3v2a, right? But of course, as I said, you can always, the basic equation is always VQ of IT. You can always use the basic equation to calculate anything. Like the quiz problem, more complicated geometry, right? For this one, let's say if somehow you didn't know we can use this one, you can still use the basic equation VQLT to derive this one. So now this half of the rectangle cross section becomes A, and Y bar is always the line passed through the centroid of this area A to the neutral surface of the entire cross section. So now this is this is a Y bar 15 because this dimension is, where is it? It's 60, yes, it should be 1/4, right? 15. And with VQAT, T should be this dimension. This dimension is given as, since this is 16, so this whole T should be 32. So this is two-way to calculate the maximum, sorry, the shear stress at point A generated by this 500. Can we always assume we can use 3v over 2a for rectangular cross section? 3v over 2a is the maximum. It's on the neutral surface of narrow rectangular cross section. Yes. It's on the neutral surface, it's the maximum. It's not at any point. At different point, I can show you later. Let me. I think I put the. Do you guys remember this one? You can check lecture notes for the details of this part. It's very important. It is very important. Let me repeat again. Our basic equation is always this one, VQ of IT, and we derive this one. Let's say if we have a B and H, right? If we have B and H, so now this is a area, and we have the I. Check the derivation part, and we plug everything in, and we get this equation. And for this is expression of shear stress on the x-plane in the y direction. How to change is a quadratic function of y, and we know that quadratic function of y and it's symmetric about neutral axis, so it's 0 at here, 0 at here, maximum magnitude at this neutral surface, and this neutral surface is y equal to 0. You plug in y equal to 0, you get 3v over 2a. So 3v over 2a, yes, we can always use when it's narrow rectangular cross-section for maximum shear stress. So I think there was one question in the past class, like, okay, when I talk about this one, I put the average. I mean, you are comparing the maximum, but now why there's average? So again, you can go back to my recording and your lecture note. The average is something I said is on this direction. In this direction, remember that I put a table in the lecture note that what if the ratio is lower than 4, lower than 0.25, and what's ratio then higher, and then higher, and then higher. And it's a table, and what is the stress change, like the maximum over average, minimum over average. So basically, the narrower the rectangular cross section is more close that the distribution in this direction is almost constant. That's why we use average subscript here. But this average really means that it's an approximation for narrow rectangular cross section in this direction. But in this direction, it's quadratic change. Why the cross-section derivation on top quarter, not top half? Cross-section. Which equation? It's just a general case. Go back to your lecture notes. This equation, this does not mean that it's a quarter. It's not half or anything. It's just general. This y can be anything. This y, it can be this distance, can be this distance, can be this distance. The y is not half of c when I derive this equation. The equation I derived in the class is for general case. It's not y equal to half of. No, it's not half. We have to use for finding max. I will make sure that the exam problem will always satisfy the narrow rectangle assumption, because anything that's not in that range is not really content of mechanics materials. So you do not need to like specifically check this, like, okay, the ratio is lower than 104. I will do my best to make sure that it's within that range, which we can use is narrow rectangular, and we can use the stress in this direction is almost uniform. The normal stress in this type of problem, how do we know when add subtract moment? Lecture, those add subtract. Lecture, I think you are asking about. Well, when is positive moment? When lecture 20. Yeah, I will post later this afternoon or tonight. For normal stress in this type of problem, how do we know when we add or subtract bending moment? For this one, you cannot really add or subtract bending moment, because bending moment here is bending moment about y-axis. Bending moment generated by this one is bending moment about z-axis. There are bending moment about different direction, about different axes. So you cannot really add or subtract bending moment. This problem we did add and subtract, and think we have this component and we have this component, but both components, they are about z-axis. If we consider this is x, this is y, all the plane in z direction, this one will generate, for this cross section, will generate a clockwise, and this one will generate counterclockwise. And of course, counterclockwise considered is positive, clockwise considered negative. So you know when to add or subtract. We only do this when it's bending moment about the same axis. For this one, we cannot really add this moment and this moment or subtract these two moments. These two moments, they are about different axes. You're welcome. If you are, so let's say for the moment when to add or subtract, I think one of the answer is about like for the stress component when to add and subtract. That determined by the sign convention. Tensile, of course, you add them. I will show you later. We will have like tensile compression, and then for compression you need to use minus something, right? So this is for point A. Any question about point A? Okay, let's move on to point B. For point B, we have normal stress caused by tension. We have normal stress caused by bending. And we have bending My and bending Mz. So bending moment itself, we cannot add, but for normal stress, we can add the normal stress caused by bending My, normal stress caused by bending Mz. So for bending about the y-axis caused by the 500 Newton, and it's obviously that the B point should be tensile. So if you really want to put a sign, the normal stress should be positive, right? The normal stress here should be positive. And for bending about this 750, it will cause bending about z-axis. Normal stress on the B point, again, tensile. So this one is also tensile, tensile, tensile. So, well, that's probably what you ask, like when to add and when to subtract. If it's all positive, of course, you add 3 terms. So normal stress caused by tension, normal stress caused by bending about y-axis, normal stress caused by bending about z-axis. Be very careful. This is not about adding the moment. You cannot add in the moment if it's bending about different axes. You can only add the stress generated by bending moment. So all positive moment arm, be careful for the bending about y-axis, bending about z-axis. This is calculated here. Bending about the y-axis, bending about z-axis. And the next part is calculating Q. Probably this is like the most confusing part. Like I didn't derive for any there's really no like equation specifically for this cross section, this point. So you need to use a VQLT to derive the equation to calculate by yourself. So let's say for this shear stress is caused by the force in the z direction, and now this becomes the top surface, this becomes the bottom surface, this is a neutral axis, and we are checking A. So now this should be the area for calculating Q. Do you guys agree with me or not? This should be the area for calculating Q. If you agree with me, now let's check. This is area, and this is A. It's 15. Since this is 60, a quarter is 15, right? This dimension is 15, and this dimension is 32, double the 16. So that's the area. 15, 32. And for the y bar is equal to the line that passes through the centroid of this area, and this is the neutral surface of entire cross section. Y bar is the distance between these two. So 15, 7.5. Make sense or not? This is 15. Half of this is 7.5. This distance between them is 15 plus 7.5. What do you mean by 10 to -9, 10 to -7? What do you mean by that? So this is a Q calculation, VQ of IT. Of course, once we have Q, V, we know it's a force in that it's a transverse force in the Z direction. Q calculate I is the moment about y-axis. T is this dimension. Because if force is applied in this way, this is a T dimension. Or let's say T, well, the same since it's rectangular. Okay. Any question for this part? No? Okay. Now let's move to point C. Point C, we have normal stress caused by tension, normal stress caused by bending, normal stress caused by bending. Bending in Y, bending in Z. Of course, we cannot add the two bending moments, but normal stress we can add. We have 3 components. Positive normal stress caused by tension. Wait, where is it? Why it's gone? I don't know what happened. Wait. Why it disappeared? We can do circular cross section, but why those zero page disappeared? One second. Let me try to do it again. Sorry, I don't know what happened. It's back. So now we have these three, and of course shear stress equal to 0 because for the shear you can see that shear here is 0, shear caused by 500 and 750 they are 0. So this is at point C. We will be only working on rectangular cross section for stress of combined loads. We can do, well, anything we talk about in previous chapter, we can always combine it here. It does not need to be rectangular cross section. It can be circular. I also put this one here. You can see that for this one is circular cross section, and we did learn how to calculate the normal stress caused by tension in circular cross section, shear stress caused by torsion in the circular cross section, and normal stress caused by bending in circular cross section, and transverse shear stress caused by transverse shear in circular cross section. We did learn all of this related to the circular cross section. So yes, of course, we can do circular cross section also. I tried to undo a few times. It didn't work. I didn't know what happened. Sometimes the notability is weird. Figuring out what cross section and orientation for use took me a long time. How to do this quickly? Cross section and orientation. Well, it depends on, so now the key thing here is back to this part. So I guess the cross section, you are talking about either bending or transverse shear, right? Because for tension compression, this is always a constant. Let's say for bending, if you have a force applied in this way, you just, as engineer, we should expect that it's bending about y-axis. Then if it's bending about y-axis, this is neutral surface, this is top and bottom surface. So and if it's this one, and we know that it's caused bending like this, so it's bending about z-axis. Now this becomes the neutral surface, and this becomes the top and bottom surface. So if it's bending about, let's say, caused by 500 about y-axis. Be careful, the moment inertia should be well, it's always BH cube. What I mean that this should be B, this should be H, right? We talk about in bending in detail. And if it's bending caused by this one, and it's bending about z-axis, now this is a neutral surface. So when you use the BH cube, this is B, this is H. You can always go back to the bending chapter to check this one. Is top surface just always the surface in tension? How you define the top and bottom surface? Let's say this is a beam. If I say this is the top surface, this is bottom surface, I bend in this way, top surface is in tension. I bend in this way, top surface is in compression. But of course, when I just talk about this one, I probably intentionally always consider, let's say, if I apply force in this way, I consider this is the top surface, this is bottom surface. If I apply force in this way, I consider this top is the bottom surface. But you guys should know when it's in tension compression. Is this clear? If I apply a force in this positive y direction, and if you consider this top surface is compression, right? So depend on bending in different direction, but I probably mix like what is top surface. If you really consider this is z direction, then this should be top surface, this should be bottom surface, but you should know what I mean. You're welcome. So, and also I guess for the cross section is also for the Q. So let's say the key part is the B point, of course. If you have a force, transverse force applied in the z direction, this is the area for Q calculation. Makes sense or not? We are trying to figure out the shear stress on this plane on the x plane in the z direction. So you can just imagine the distribution on this in this direction, in the z direction should be 0, 0, maximum and neutral surface quadratic in between. And for B point, we do need to use VQLIT to calculate, and the Q here is this one. The neutral axis changed. Yes, neutral axis changed. Neutral axis is let me demonstrate using this one. When the Q when we are looking at the area for Q would be half. What do you mean by Q would be half?
So you were saying for if we're looking at point B and we're trying to find the shear, that area would be the quarter or whatever, the distance from, yeah, the 15 or whatever it was. For if we were looking at point A instead, it would be it would be 30 millimeters,
Yes.
which is half.
Yes.
Okay.
I did the calculation here. So let's say if you don't want to use this equation that I derived in class, you want to calculate by yourself using the original equation VQLT. So now this is the area for calculating Q. And this is 32, yes. Oh no, 30. The neutral axis change for, let me explain that one. Let's say this is the beam. I have cat hair everywhere. And if it's a force in the, let's say if it's a force in this direction, and then it's bending like this. Let's say if the force is this, then this is a neutral surface. This is a neutral axis. But if it's a force applied in this way, then it's bending like this, right? This is a new this axis of bending. It's bending about the axis that is out of screen. So now this is the neutral surface. So basically, if I put on the graph, for the force applied in the z direction, it's bending about the y-axis, and this is a neutral surface. If for the force that is applied in the negative y direction, or let's say just in general in the y direction, it's bending about z-axis. Now, this is a neutral surface, neutral axis. Not exact neutral axis. Neutral axis is in the actual direction, but yeah, this is the line of neutral axis on the cross section. Neutral surface on the cross section. When we're looking at different orientation, which measurement doesn't become? What do you mean by which measurement doesn't become? So basically, neutral surface is perpendicular to the applied force. Well, you can say it in that way, but I can also say that, do you remember when we taught that in the beam chapter, I just apply a bending moment here directly. I don't apply a force. I apply a couple or a moment. Then how can you say that it's always perpendicular to force? There's no force here, right? So a better way to understand that, let's say if it's bending in this way, it's bending about z-axis, the neutral surface is here, is in the direction of the axis that is bending about, right? Let's say same thing. If I apply a couple or a moment about z-axis, this is in the z-axis direction. This is the neutral surface on the cross section. If we are applying a force in the z direction, then it's bending about y-axis, and this is y-axis. Neutral surface, we can say that it's in the direction of the axis bending about. Well, you can say that it's perpendicular to the force applied, but I think a better way to explain this is that the neutral surface on the cross section is always in the direction of the axis it's bending about, right? Because I can apply force generated this bending moment. I can also apply a couple here directly. There's no force. I mean the thickness T, thickness T. Which measurement does T become? When we look at different orientation. Okay, good question. The better way is just check the original derivation. If the force is applied in this direction, transverse force, this is a T, right? This is a T, dQLT. I don't have the complete lecture note of this section, but you can always check your own lecture notes in this topic. There's very detailed derivation, and there's a graph of like a trapezoid shape. And let's say if you want to check the shear stress here, now this dimension is a T. And if I want to check this, hi, someone is here. So let's say if it's a force applied in this direction, if I'm checking any point on this line, this is T. If I move downward, check any point on this line, this is T. It is clear or not? But if I apply a force in this direction and check some point here, then this becomes a T. I think a better way is that you check the original action node. It can help you understand what is T, what is Q, and what is Y bar, what is A.
All right, so can you translate that to the problem where I'm trying to visualize it.
Yeah, which problem?
Yeah, the thickness for at point B.
So let's say the T for the transverse shear stress caused by transverse force. If it's a force applied in the Z direction, and we are checking the point B, this dimension is T. Make sense or not? This dimension is T. If we are checking this force and let's assume that I asked, my cat. Let's assume that I ask a point here for this force. Now this becomes the T. This becomes the area. And this dimension is the T. Thickness is always perpendicular to the platform. You just really want like, okay, something is always this like fixed relation. I think it's better just to understand. Yes, you can say that T dimension is perpendicular to the force applied, but I think it's better just not memorize any kind of like which dimension should be perpendicular to what thing, what should be parallel to something. You will get confused in the exam. It's better, always better to understand from the basics, Let's say for force of the 500, this is the area for calculating Q, and your force goes in this direction. So this is a T. This is a T, right? And if I'm talking about this 750 and the shear stress change in this direction and start from 0 here, stop at 0 here, and let's say random point is considered a C point. Now this becomes the area for calculating Q, and this is the T. Yes, of course. I will, for the circular cross section, I will post this one this afternoon or tonight, because we learned how to calculate normal stress, shear stress, general by tension compression, transverse shear, bending, torsion for circular cross section in all the previous chapter. So it is perfectly okay to calculate. We already have everything we learned for calculating circular cross section. This nothing new here. Yes, we can check it now. So for this one, let's say we have two forces applied at point A and B, and the diameter is given. Calculate principal stress, maximum shear stress at point H and K. Let's check H point first. So again, let's separate 250, sorry, 2500, 600, these two forces. This one, of course, it will generate compression. So this comes back to somebody ask like when to add a stress component, when to subtract a stress component. Now, since it's compression, of course, it's subtracted. No, also you can just like you add all the stress component, but stress component itself, it can be positive and negative, right? Stress components has sign convention itself. So you can say that you add all the stress component, but stress itself has positive and negative. So this one, of course, there are negative here and negative here. Beautiful. For this 600, it can generate bending about x-axis. Bending about x-axis. So you just imagine that it's equivalent of having force applied here, and now this is the moment arm. So it's bending about x-axis, and of course, it will generate a torsion, right? When you apply a force here, if this structure is not that rigid, it will generate rotation about. So this is about z-axis. So this is the torsion here, and of course this has transverse shear because it is in the y direction. So let's do it separately for the bending. At H point, if it's bending about the x-axis, H point is a top point. H point is a top point. It has positive tensile normal stress, right? Positive tensile normal stress. K point is on the neutral surface, it's 0 for normal stress caused by bending mx. Torsion, remember the stress distribution? Both H and K, they're on the outer surface, they have the maximum magnitude of the shear stress caused by torsion. All of them, they are non-zero, they are the maximum. Transverse shear at H point is considered as top point because if you consider a force applied here, H point is the top point, K point is the neutral surface. So H point is 0, K point is the maximum. And we also derived if it's circular cross section, what is the maximum shear stress caused by transverse shear? We derived. So now let's calculate one by one. For the H point, we have normal stress from two. One is compression, which is a negative value. One is bending, which should be a positive value. Negative. Positive. All right. Shear stress, we have this one. Remember TC over J? So this chapter is more of combining everything we learned in the previous chapter, start from the beginning of the semester. So even though our exam is not a cumulative, but you do need to understand all the chapter in the previous semester. TC over J. TCJ. For the torque, I want to emphasize here, this is the 600 for the force, and this should be the distance for generating this torque. So torque equal to this force times this distance. 600 times 2.5. In which chapter? This is chapter 8. You can check the textbook. Stresses under combined forces, combined blows. Yes. Chapter 8. And let's ignore this part because I use Mohr circle for calculating principal stresses and maximum shear stress. We can use equation. I will update this part. But this is the same as using equation because maximum stress is the half of sigma x plus sigma y, and square root that component is the exact same, but we just don't use the circle. So I can update this part later. Calculating the maximum principal stress, minimum principal stress, maximum principal stress, minimum principal stress, maximum shear stress, based on the stress component we just calculated. And for the K point, we have normal stress, just 1. So it's from compression. This one is easy. 1 from compression, right? And for calculating shear stress, we have 2. The shear stress caused by torsion, this one is simple because TC over J is on the outer surface. So it's maximum TC over J. You use the rho equal to C. Let's talk about this one first. TC over J. This part is simple. The part that get complicated is the shear stress, because now if you consider a force applied here, and K is on the neutral surface, and we want to calculate the shear stress, we can use, I guess I didn't derive in this class, but we can always use VQ by T. So this should be the area we calculate the Q. It's half of the circle. You guys know how to calculate half of the circle, right? Circular cross section. For the Y bar, again, just Google it. Where is the location of the centroid of half circle? So that is the Y bar. So this is the Q. And of course, since it's a force applied in this way, and we are considering calculating shear stress generate here, now this dimension is a T. So T is double the radius. V, Q, I, T. This is the centroid of the half circle to the neutral surface of entire cross section, which is this distance. And you guys can Google check where is the location of the centroid of half circle. You should show something like this. Where is K at? K is at here. So if you draw find the cross section, K is here. Yes, we'll be given the general information. Yes. You don't memorize anything. You don't need to memorize this exam. All the tests in our class is not about memorizing anything, it's about understanding. Why there's no bending at K? There is bending moment on this cross section. It does have bending moment on this cross section. It's just the normal stress generated by bending moment at K equal to 0 because K is on the neutral surface. We do have bending moment on this cross section. It's just normal stress generated by bending moment at K equal to 0. Does this make sense or not? Okay. Any other question about this problem? I will post this one after class this afternoon or tonight. Any question for?
What would the thickness be in this one?
Here.
Okay.
Yeah, so let's say the force is applied in this direction, right? This is a transverse force, and your shear, you are trying to figure out the shear stress goes how it change in this direction, and of course it start from 0 here and start from and 0 here, and how to change in between use VQ of IT. So when it goes in this direction, and let's say if I'm asking this point, then this should be the area for calculating Q. And now let's say if I'm asking about this point, then this should be the area of calculating Q. And I move to the middle point. Now the half circle is the one we should use for calculating Q. And of course, when force goes in this way, this is a T. This is a T. It's a diameter. It's a diameter. Does this make sense or not?
Yes, thank you.
You're welcome.
So I had one more question.
Yeah.
When we were doing the principal stresses and we had the different sigmas like sigma X and sigma Y, I was wondering in the previous questions, like the one that we had before with the beam, where would a force be considered sigma Y in that like 3D space? It's theoretical, not kind of more to the question, but just
Oh,
trying to
okay.
understand. Yeah.
Good question. So for tension compression and bending, the normal stress generated by tension compression and bending for this one is always in the x direction. Makes sense or not? So it should always be sigma x. So let's say this is the beam. I apply tension compression. The normal stress should be in the x direction. So let's say x direction is x. So it always should be sigma x. And bending, no matter I bend in this way, or bending in, I don't know how to, yeah, it's always the normal stress in the x direction, so it's still sigma x. How to generate sigma y? Let's say upward is positive y direction. I fix the bottom part. There's a boundary condition at the bottom part. I use a support at the bottom part or clamped on the bottom part. I apply a force in the y direction. This will generate a compression, sigma y, negative compressive normal stress, sigma y. Or I pull the top surface, and also clamped at the bottom surface, and this will generate a positive sigma y. Does this make sense or not? But at bending, no matter which axis bending about, it's always the normal stress in the x direction. Right? To really generate sigma y's, you always like push it or pull it in the y direction. But normally, I mean, why would you want to clamp the beam at the bottom part and apply a force? I mean, in civil engineering, yes. Yes, in civil engineering, you clamp the bottom part and then you apply force, and it's a compression sigma y, yes.
Thank you.
You're welcome. No normal stress generate, okay, because C equal to 0. Yes. We do have bending moment on the cross section, but this one is a neutral surface for this force, right? K is on the neutral surface. That's why the normal stress generated by bending is 0, but doesn't mean that bending moment on this cross section is 0. Bending moment on this cross section is not 0.
Excuse me?
Yeah.
So that question says to determine the principal stresses and maximum shearing stress.
Yes.
Will we be expected, because we've only worked with principal stresses and maximum shearing in 2 dimensions. How would we go about that in the 3rd dimension?
Good question. Yes, we only talk about the normal stress and the shear stress, sorry, principal stress and maximum shear stress for plane stress situation for 2 dimension. This is a 3D problem, but if you check every point we calculate here, it's still only in 2 dimension. This nothing. So let's put a subscript here. Let's use a different color. Let's use purple to make it. So let's say x-axis, z-axis. So the normal stress is sigma z, right? Make sense? And the tau generate at H point, it should be on the z plane in the x direction. Zx. So do you agree with me that yes, it's a 3D problem, but we only have non-zero stress component in 2 dimensions, x direction and z direction. There's nothing in the y direction. So we can solve it. Make sense or not? Did that answer your question?
Yeah, I wanted you to like walk us through solving it.
So let's say this is a sigma z. This is a tau zx. Do you agree this become 2D problem now? Everything else, they are 0. Everything else, they are 0. So it becomes 2D problem. No, I cannot erase this one. So this becomes plus 0 because let's say this is 0. Make sense or not? And let's write. It's exactly the same thing. Half of plus 0 plus minus square root of when you use plus, it's sigma 1. When you use minus, it's sigma 2. Does this make sense or not? You need to give me some feedback.
Makes sense.
So we just put 0 for anytime we see sigma on y.
Whenever there's for the thing we calculate is all the non-zero term, right? For the thing we didn't calculate, it's basically it means that that stress component is 0. We as I just explained, like why we have 0 here, we didn't calculate, it's 0. So if you really want to like substitute use that equation, like what is that component? If it's not calculated, it's 0.
Makes sense. Thank you.
Yeah, you're welcome. And same thing for the K point, we have sigma. Let's put the subscript here. So for the K point, sigma is still in the x direction, which is in z direction. So, and for the K point, for the shear stress caused by torsion is in the z plane in the y direction. Zy. Again, yes, it's a 3D problem, but we only have everything in the z and y axis. So it becomes the 2D problem in our calculation for principal stresses and maximum shear stress. I will update this part after class. So because this method I use Mohr circle, but it's we didn't have time to cover the Mohr circle this semester. But it's the same. I can use the equation method to calculate maximum shear stress and maximum principal stress, minimum principal stresses. It's the same thing. Any other question? So essentially you are saying that a third dimension doesn't impact everything in the third dimension, they are 0. Everything in the third dimension, they are 0. Then it becomes a 2D problem. Remember when we talk about a plane stress problem, 2D problem, is the stress in the third dimension becomes 0. So we consider it's a 2D problem. Same thing here. Everything is about in the z direction and y direction. So everything in the x direction is at 0. So third direction to 0 becomes 2D problem. That's square element. Is there any bonus question on the final exam? I don't know. I haven't made the exam yet. Does square element represent point K. That's square element. What is a square element? So this is, sorry, what? This is for the static stress at point H. You see that I put this one here. This is normal stress in Z direction. This is shear stress in the ZX. Sorry, this is ZX. Right. The third direction is the Y direction, which everything are 0. So this is the square element for H point. And this is a square element. This is a square element for the K point. So now we calculate this one. I put it here. And shear stress, I put it here. And this is everything about Z and ZY axis. So the X axis becomes the third direction. You're welcome. Oh my God, that makes sense now. What makes sense now? Any other question? Any question you want to ask? I know this part is a little bit more complicated because it does require your solid understanding in all the previous chapters. It includes tension, compression, bending, torsion, transverse shear, principal stress, maximum shear stress. It's chapter 8 is like combination of all the previous 7 chapters. So that's why it is complicated. So any question you want to ask? So only cross section we may see on the exam is circular. Yes, circular or rectangular cross section. Yes, for this chapter, for chapter 8, yes. But remember the quiz problem? We ask you to calculate just only the shear stress caused by the transverse shear stress, transverse shear force. That one, it can be really any cross section, and we intentionally test you if you know how to find the Q, how to find the Y bar, how to find the A, those kind of things. So for that one, I can use any cross section, but for this stresses and combined loads, it's only either rectangular cross section or circular cross section. If it's rectangular, it won't rotate like some amount degree or something. What do you mean by rotate some amount of degree? Or something like triangle. Sorry, I don't know what I mean. Why we can treat it at 2D because the other direction is 0. Yes. For 3D problem, if we only have non-zero stress component in 2 dimension and the third dimension in 0, we can consider it a 2D problem. This is always correct in general situation. It's not just for this class, for any class. With a circle. Do you remember any homework that the most recent ones to help us review this with a circle? What do you mean by this? Circular cross section? More circle is not required for this exam. We didn't really have time to cover this one. But if you are talking about the circular cross section, I can post this one, and I will try to find out if I can find more problems you can review. How can we prevent ourselves from missing any stress components due to the force applied to the beam? Also quiz 3 before the exam, so we can look over answers and know how we did. For the quiz 3 solution, I already talked about in the class. You check my recordings. I posted the recordings. Yeah. I will talk to TA. I think he graded half. I'll push him this afternoon. I will try to push him to finish grading before Wednesday, before exam 3. Good question. What we can do to prevent ourselves missing any stress component due to, again, this is always the key. This is always the thing I would emphasize in the higher level class, because we also testing this kind of question in the higher level class. Like when we start aerospace structure, this is always the first question we ask. This type of question, we make it more complicated, of course. And it's very easy to see students like always missing some component and have some extra component that should not be there. Let's say if I'm asking about this A point and somehow some student calculate the shear stress caused by this transfer force, it should be 0, but somehow they calculate it and they put it there. So the key thing is that you make it very clear, something like this. So we have 3 forces. This force generate tension, this force generate shear and bending, this force generate shear and bending about different axes. And for these different forces as general term, what kind of stress they generate, and based on the stress distribution, do they at different location, are they 0 or some non-zero value? So I would say this is the key part for calculating this one to prevent you guys from missing any components or adding actual non-existent components. I have a general question. In the future class, will we ever calculate the torsion of rectangle? Yes. In the aerospace structure, we have a chapter calculate about the torsion about rectangular, torsion about the ellipse shape, torsion about I-beam, torsion about any random cross-section geometry. We have a whole chapter talking about that for different cross-section. It's not only circular anymore. All can regular cross-section never experienced in no. Torsion can applied in any shape cross-section. We know the bending is positive and negative in this table. Well, you can always put the positive or negative in here. I didn't, but you can always put it there. But it's not that difficult to check, right? So let's say for this force, you know everything on this side should be tension. Everything on this side should be compression. And for this force generate bending, this is neutral surface. Everything above should be tension. Everything below should be compression. So based on the force direction and the location of the point, you know when is tension compression. But of course, you can always use my of y. Let's make it simpler. The simpler way is that for the force, checking the force direction and checking the point location of the point, we know which one is positive, which one is negative, and we can put a sign there. I think that is much easier for you guys to understand. I know this can be calculated, but I mean that we don't see the rectangle being rotated on the rotate like this. This can be, but I mean we don't see the rectangle cross section rotate. I said this is not for the picture. Nice picture, by the way. For the picture you put it there, it's torsion. It's torsion. Let's say you have a rectangular cross section, right? You are rotating like this. This is a torque. This is not bending anymore. This is torque. And I talked about that in our mechanics materials. We only talk about torsion with circular cross section. For any other cross section, you don't need to worry about it for this exam. It's in your future class. Did I answer your question? Any other question? Well, it's time. So if you have any question about the exam, come to my office hour. If you need any extra office hour, email me, let me know. I can have extra office hour for help you guys prepare for the exam. So I will switch the Zoom link to the office hour Zoom link. So please join. My cat is here. And thank you for coming and have a great day. After that, are we done for this class? Yes, but if you want some extra class, I can also do it also. I can do some extra class after exam if you really want. No more class on Friday. If you want, I can have class on Friday. Depend on you. No class on Wednesday. Yes. Class on Wednesday is used for you guys preparing for the exam. Oh, nice. Enough to have more classes. Yeah. Any other question? Okay. Thank you. And have a great day. I'm gonna switch the office on Zoom link.